You think you're scanning the universe right now, but here's the uncomfortable truth. Your search for intelligent life is barely a search at all. It's more like a tiny test patch on a surface so huge you can't really imagine it. Let's start with the scale, because if you don't feel how extreme the numbers are, nothing else will land. Your own galaxy, the Milky Way, holds around 100 billion stars, maybe more, and there are at least that many planets, probably several times more, because many stars host multiple worlds. Then you step back and you realize the observable universe contains at least 100 billion galaxies, each with its own huge population of stars and planets. Multiply those together and you get something like a 1 with 22 zeros after it. That's the rough count of stars you're dealing with. When you say, maybe there's another Earth out there, that sounds reasonable. But when you ask, how do we actually check? The problem becomes almost absurd. So what does searching really mean in that context? Right now, when you look for intelligent life, you mostly listen for radio signals or look for very specific kinds of light from very specific targets for limited periods of time. You're not sweeping the whole sky at once, you're not checking every star in every direction, across every frequency all the time. You pick small patches, narrow bands and short windows. Think about what that implies. People sometimes say, we've listened and heard nothing, so maybe nobody is out there. But the honest description is closer to this. You've checked a tiny fraction of all the options. A better way to picture it is that you have sampled a microscopic part of Earth's oceans and then tried to draw a conclusion about all marine life. You dip one glass of water from one spot, you look inside, you see no fish, and then you try to generalize from that. Technically you did look, but that no answer has almost no weight. Now zoom in on the physics that makes this so hard. When a civilization sends out radio waves, those waves don't stay concentrated. They spread out in all directions, forming a bigger and bigger sphere as time passes. The same original energy has to cover that growing surface, so the energy in any small area drops fast. It falls with the square of the distance. Double the distance, and the signal in any one small patch is 4 times weaker. Push the distance to 10 times, and the signal in that patch is 100 times weaker. At interstellar scales, that drop is brutal. Put yourself at the receiving end. Here on Earth, your radio telescopes are trying to pick up signals that might have left another star hundreds or thousands of light years away. By the time that kind of signal reaches you, if it ever does, its strength is tiny, buried inside a lot of natural noise from your own planet, your own technology, and the wider cosmos. Your instruments have to figure out whether there is a real deliberate pattern hiding inside that noise or whether it's just random static. That is not easy. Even your own old TV and radio broadcasts, which you like to imagine racing across the galaxy, fade into the background after just a few light years. Beyond that, they look like nothing special. So if aliens are anything like you, if they spent what period of time blasting out loud, messy radio and TV signals, most of that leakage is basically invisible at the kind of distances you care about. To see something clearly from far away, they would have to be using deliberate, powerful, focused transmissions, aimed more or less in your direction, or at least in your general area, and they would have to keep doing it for long periods. That already assumes a lot about their behavior, their technology, and their motivations. Now, even if those conditions lined up, you hit another problem. Your coverage of the sky and the spectrum is tiny. Most SETI work right now looks at narrow ranges of radio frequencies, often chosen because the universe is relatively quiet there, which makes artificial signals easier to spot. That's smart, but it means you're ignoring huge parts of the spectrum. On top of that, you don't watch the whole sky all the time. You point your dishes at particular stars or regions for hours, maybe days, then you move on. So ask yourself this: what are the chances that an alien civilization using a specific frequency at a specific time sends out a signal that happens to cross the tiny patch of sky your telescope is staring at during the exact few hours you're listening and in a format your software is actually looking for? The timing, the direction, the frequency, and the signal type all have to line up, If any one of those things is off, if they broadcast yesterday, or on a different band, or from a star you're not targeting, or with a modulation you don't recognize, then for you they don't exist. This is the bottom line of the first problem. The physical scale of the search makes absence of evidence almost meaningless. You have a universe with on the order of 10 billion trillion stars. You have signals that fade quickly with distance. You have instruments that only watch small patches of sky in narrow bands and short time windows, and you have no idea what exact kind of signal you should even expect. Under those conditions, we haven't seen anything yet. Does not tell you much about whether anyone is out there. It mainly tells you that your search so far is extremely limited. And here's where the tension really starts to rise. Because everything we just talked about is the easy part. This is just about how far you can listen, how sensitive your gear is, and how much sky you can cover. You can always imagine building bigger telescopes, linking more antennas, improving your receivers, throwing more computing power at the data. Those are engineering problems, hard but not impossible. But what if, even after you push your instruments to their limit, there is a deeper barrier you cannot bypass? What if the real problem is not how hard you listen, but how slowly information is allowed to travel in the first place? What if the speed of light itself is the wall, turning the galaxy into a place where, by the time you hear anyone, you're only listening to their past, long after they are gone? Even if the galaxy is crowded with civilizations, you are talking to their ghosts. When you look up at the night sky, you're not seeing now, you're seeing a time delay, and that delay is not small. If a star is 1,000 light years away, the light you see tonight left that star around the year 1025, before telescopes existed, before modern science existed, before most of your history even happened. You are looking at old news, frozen in transit. Any signal you send back today, even with your best transmitters, will not reach that star until the year 3025. So every time you point a telescope at a distant system and ask, are they there? You're really asking, were they there 1,000 years ago? And you will not get an answer to, are they there now, for another 1,000 years? So here's the first hard question. Even if intelligent life is common, how often do your time windows line up? Think about the age of the universe. Around 13.8 billion years, and then drop on top of that the likely lifetime of a technological civilization. Be generous. Say 10,000 years of being radio loud, building tech, using energy on a big scale, leaving detectable fingerprints. 10,000 years feels long to you, but compared to billions, it is tiny. It is a thin line on a huge timeline. That means most civilizations, if they appear at random points in cosmic history, will shine for a short time and then go dark. Maybe they collapse, maybe they go quiet. Maybe they change their technology in ways you can't detect. The chance that your short active phase overlaps with their short active phase at the right distance is not good. It is like trying to sync two brief flashes on a huge clock without planning, without coordination, just random timing. Most of the time, the flashes do not overlap. So even if the galaxy has had thousands of civilizations spread across its history, the number that are on right now, within a reasonable distance and overlapping your own brief technological phase, could easily be zero. At this point, you might push back and say, fine, but as long as they send strong signals, we should still see something, right? That's where the second brutal factor comes in, the way signals behave over long distances. Radio waves spread out as they travel, we already talked about that. The energy has to cover a larger and larger area, so the intensity at any single point drops sharply with distance. But that's not the only problem. Those waves also have to pass through actual material, thin gas, dust, free electrons, all floating between the stars. Over light years and light years, this material can shatter and smear the signal, especially at lower frequencies. It stretches pulses, distorts them and weakens them even more. On top of that, your detectors are not sitting in silence. Your own planet produces radio noise, from communication networks, from electronic, from the atmosphere. The galaxy itself produces background radio emission from things like electrons spiraling around magnetic fields, from star-forming regions, from the center of the galaxy. When you point a radio telescope at the sky, you're not listening to a clean channel, you're listening to a crowded one with a lot of static already built in. Now drop a real example into that environment, a normal TV broadcast or radar signal, or Wi-Fi spillover from some alien world. At a few light years, maybe you could still pick it out with very sensitive gear. At tens or hundreds of light years, it becomes so weak and so mixed into everything else that it is effectively invisible. To you, it just becomes more random noise. So if you are hoping to detect aliens by the casual, unintentional leakage of their technology, the way your own radio and TV have leaked into space, the physics is against you. You might respond, okay, then they just have to try harder, they can send tight beams, powerful focused transmissions straight at us. Maybe, but now you are stacking assumptions. You're assuming they know about you, that they decide to spend large amounts of energy shouting in your direction, that they stay stable for long enough to keep doing it, and that you are listening at the right time and frequency. If any of those conditions fail, you go back to silence. So here is the next twist. Even if all that lines up, even if some civilization chooses to talk directly, you still run into a wall that no amount of clever engineering has broken: the speed of light. Relativity, as far as we can test it, says this very clearly. Nothing that carries information goes faster than light in a vacuum. No signal, no particle, no clever trick can beat that limit. That speed is fast on human scales. You can cross the distance from Earth to the Moon in just over a second, but it is slow on galactic scales. Light takes more than 8 minutes just to travel from the Sun to Earth, hours to reach the outer planets, years to reach nearby stars, and thousands of years to cross large parts of the Milky Way. Now imagine you actually get a clear signal from a civilization 1,000 light years away. The day you receive it, that message is already 1,000 years old. You write a reply, you build a powerful transmitter, you send your answer back. It takes another 1,000 years to arrive. So the fastest possible round-trip conversation, from hello to we heard you, takes about 2,000 years. Nobody on either side will live to hear the response. Even if their civilization survives, the people who sent the original signal will be long gone. Their language may have changed, their technology, their entire culture may be unrecognizable. This is not just a practical inconvenience, it is a fundamental barrier. There is no warp drive switch you can flip to make the speed limit go away. Every time someone imagines faster than light communication, they run into deep problems, time loops, causality violations, paradoxes where effect happens before cause. Physics, as we understand it, shuts those doors. Could there be unknown physics that allows some kind of shortcut maybe? But you cannot plan your search strategy on maybe the laws of nature we see everywhere are secretly wrong. Right now, the only honest position is this: light speed is a hard ceiling for information. So what does that mean for your dream of chatting with aliens, of doing live interviews with another intelligence on some distant world? It means that even in the best case, those conversations are really one-way messages to the future, or answers to questions from the deep past. You're not talking to them, you're talking to a recording of them, a version of their civilization that existed centuries or millennia ago. And if they answer, they are talking to a version of you that no longer exists. Put it all together. You're observing the universe with a built-in time delay. You're listening for very weak signals that fade and get distorted over huge distances. You are overlapping with other civilizations only in tiny random slices of time, and you are bound by a speed limit that stretches every attempt at dialogue into thousands of years. The galaxy might be full of intelligent life, but the combination of short technological lifetimes, signal decay, and the light speed wall turns it into something like a museum, full of distant exhibits you can see, maybe even detect in detail one day, but not something you can have a live conversation with. And here comes the next uncomfortable question. Even if you somehow beat the odds in time and distance, even if you catch a clear signal across that light speed gulf, how many planets are actually good enough to host life long enough and stable enough for intelligence to appear in the first place and stay around? Yes, there are thousands of planets. That doesn't mean there are thousands of Earths. You hear the number and it sounds huge. As of late 2025, astronomers have confirmed a bit over 6,000 exoplanets in more than 4,500 star systems, with thousands more strong candidates waiting to be checked. That sounds like the universe is throwing planets at you non-stop, and in a sense it is. So it's easy to jump straight to, okay, if planets are everywhere, intelligent life must be everywhere too. But that jump is exactly where the trap is. The universe is full of worlds, yes, but the kind of world that can host long-term, stable, complex life like yours might be incredibly rare. First, you need to understand how you're even finding these planets. Most of them are found using two main methods: transits and radial velocity. Transit means you are watching a star's brightness over time, and you look for tiny dips when a planet passes in front of the star and blocks a bit of its light. Radial velocity means you watch the star's light very carefully, and you look for a small wobble caused by the gravity of an orbiting planet pulling the star slightly back and forth. Both methods are powerful, but they have biases built in. These tools are best at finding big planets, close to their stars, moving fast. A huge planet that orbits very close will cause a deep, frequent dip in brightness, and a strong, obvious wobble, so it jumps out of the data. These are the hot Jupiters and other close-in giants that you keep seeing in exoplanet catalogues. They are not like Earth. They are massive. They are often scorching. Their year might be just a few days long. They are easy to detect, so they dominate your lists. The kind of planet you actually care about, something roughly Earth-sized, not too close, in a one-yearish orbit, is much harder. The transit signal is tiny, the dip in starlight is small, and it only happens once per orbit. That means if the planet takes 1 year to go around its star, you get one dip per year. To be sure it is real, you want to see that dip repeat, again and again, so you need many years of clean data, with very high precision for each target star. That is slow, it is expensive, and it's easy to lose the signal in noise. So already your picture of how common Earth-like planets are is skewed. You're seeing a universe full of big, hot, weird worlds, not because those are the only ones that exist, but because those are the ones you can detect most easily with current methods. When you hear thousands of planets, you should mentally add, but most of what we've seen are the loud, obvious ones, not the subtle ones that might matter most for life. And even if you find a planet in the so-called habitable zone, that label is much weaker than it sounds. The habitable zone is just the range of distances from a star where, in simple models, a planet could have liquid water on its surface if everything else goes right. It is a temperature range, nothing more. Being the right distance is just the first filter, and it is a very rough filter. To actually be habitable long-term, a planet needs a lot more. It needs an atmosphere that is thick enough to hold heat, but not so thick that it turns into a pressure cooker. That atmosphere has to be made of the right stuff, with greenhouse gases in the right balance, and it has to be stable over hundreds of millions of years. The planet likely needs plate tectonics, moving crust that recycles carbon and regulates climate on long time scales. Without that, you can get runaway freezing or runaway heating. You also want a magnetic field generated by a molten convecting core to shield the surface from the charged particles streaming from the star. Without a magnetic field, a strong stellar wind can slowly strip away the atmosphere, like what probably happened to Mars. On top of that, you need orbital stability. The planet's path around the star can't vary too wildly, or its seasons and climate will swing too hard for complex life to handle. All of these conditions need to hold not just for a moment, but for billions of years, because evolution is slow. Now look at what we're actually seeing when we study exoplanet systems in detail, especially with instruments like JWST and the best ground-based telescopes. We are not seeing neat copies of the solar system. We're seeing ultra-hot planets that are heated to thousands of degrees because they hug their stars at tiny distances. We see hell planets with dayside temperatures that melt rock and atmospheres loaded with vaporized minerals. We see worlds stretched into slightly distorted shapes by tidal forces, not even nicely spherical. We see systems where multiple planets are jammed very close together, all orbiting in just a few days with complex gravitational interactions. In other words, real planetary systems are messy. They are wild. They do not look like the clean diagrams in old textbooks, with evenly spaced circular orbits and calm climates. Many systems show signs of violent pasts, planets migrating inward or outward, worlds colliding, gas giants sweeping through and disrupting smaller rocky bodies. When you run simulations of planet formation, you see that kind of chaos is normal, and a calm, long-term stable setup like the solar system might be the exception, not the rule. So ask yourself this: out of all these systems we're starting to see, how many have a small rocky planet in a stable orbit, at the right distance with a long-lived atmosphere, a protective magnetic field, active geology, and a climate that stays in the narrow band where liquid water and complex chemistry can survive for billions of years? The honest answer right now is, we don't know, but it does not look like most of them. It looks more like a tiny fraction, maybe very tiny. And remember, having liquid water and a decent climate does not guarantee anything about intelligence. Those are just the starting conditions for simple life. The universe is saying, even to get the stage ready, you need a lot of rare things to line up, and you need them to stay lined up for a very long time. That should already make you nervous about how many true Earth analogues are really out there. Here's the uncomfortable conclusion for this part. Planets are common, no question, the galaxy is full of them. But Earth-like, long-term, stable, biologically friendly planets that sit in the right zone, keep their atmospheres, keep their magnetic fields, keep their plate tectonics and avoid catastrophic disruptions, might be vanishingly rare. And even on those rare worlds, there is still another filter waiting, maybe the harshest one of all. Because even if you hand the universe a perfect Earth clone, with oceans, continents, and a stable sky, you still have to get life started from non-living chemistry. How hard is that jump, really? And what if that step, not the planets themselves, is where almost everyone fails? Turning raw chemistry into a living cell may be so hard that it happened once in the entire galaxy. On Earth, life shows up fast, shockingly fast, once the planet cools down enough to have stable oceans. The oldest signs of life we've found are more than 3.5 billion years old, maybe even older, while Earth itself is about 4.5 billion years old. So in rough terms, within a few 100 million years of the surface becoming calm enough, something living appears. At first glance, that sounds comforting. You look at that and think, oh, so as soon as you get water and rocks and some simple chemistry, life just starts, it's automatic. But here's the problem. You only have one world where you know life started from scratch, one data point, one roll of the dice. A single fast success does not tell you whether the odds were 1 in 10 or 1 in a trillion because you're observing from the winning ticket. You don't see all the universes or all the alternate timelines where Earth stayed sterile, you only see the one where it worked. So you can't read probability off that one example, no matter how much you want to. So what is that first step actually like, the jump from non-living chemistry to something that can grow, copy itself and evolve? We have a name for that step, abiogenesis, the origin of life from non-life. And right now it is still mostly a black box. In labs we can do impressive things, we can create amino acids, the building blocks of proteins from simple gases and energy. We can make lipids, molecules that naturally form little bubbles and membranes in water. We can make short strands of RNA, which can store information and sometimes even help reactions along. That sounds like progress, and it is, but notice what's missing. We cannot take a realistic early Earth mix of chemicals, put it in a tank, leave it under natural conditions, and watch a fully self-sustaining, self-replicating cell appear. Something that eats, grows, and divides on its own. We have models, we have partial pathways, we have lots of maybe it went like this, but we do not have a complete, experimentally verified chain, from raw soup to real cell. There is a huge gap between simple organic molecules exist, and there is a cell that can evolve for billions of years. So if we're honest, we don't know whether that gap is easy to cross or almost impossible. It could be that once you have water and basic chemistry, life is nearly guaranteed. It just clicks into place over and over. Or it could be that you need a very specific rare sequence of accidents, the right molecules, in the right order, in the right environment for a long time, without getting wiped out. Both possibilities fit the data we have right now. Look at how many things had to line up on early Earth. You needed stable oceans, not frozen solid, not boiled away, staying around for millions of years. You needed constant energy sources, sunlight at the surface or chemical gradients at hydrothermal vents on the seafloor, where hot, mineral-rich water meets cold ocean water. You needed solid surfaces, like mineral crystals or clay, where molecules could stick, gather, and react more easily than in open water. You needed the right mix of elements and compounds, not too oxidizing, not too destructive, so the first fragile structures weren't immediately torn apart. On top of that, you needed time, uninterrupted. No full global sterilization that boiled the oceans, no total loss of atmosphere, no permanent freeze that turned the whole planet into a dead ice ball. Earth came close to disaster several times, but it seems like life either started before those events and survived, or started again aimed and then managed to hang on. That balance, just stable enough, just active enough, might be much rarer than you think. So how do you test whether life is easy or hard to start? You need a second example. You need another world where life began independently, not seeded from Earth. That's why our own solar system suddenly becomes a kind of laboratory for this question. Mars, long ago, had rivers, lakes, maybe even a northern ocean. Europa and Enceladus, moons of Jupiter and Saturn, hold subsurface oceans under ice, heated from below. Titan has complex organic chemistry on its surface and in its atmosphere. We send rovers to Mars, we drill into the soil, we look for organics, for patterns that scream biology instead of random chemistry. We send spacecraft past Europa and Enceladus. We sample the plumes that spray out from cracks in the ice. We study their chemistry in detail. We point telescopes at their atmospheres, hunting for gases and combinations that life tends to produce. So far, we have found interesting hints, complex molecules, maybe fossil structures, but we have not found a clean, undeniable, this is life and it started here on its own, separate from Earth. No slam-dunk second genesis. And that silence should bother you at least a little. Yes, the search is still in an early phase. Yes, we have barely scratched the surface of these worlds, literally. But the fact remains, you have exactly one confirmed biosphere, on one planet, around one star. For all your exploration so far, you do not have proof that life pops up easily wherever it gets the chance. Until you see life arise twice, independently, you are stuck with the possibility that the origin of life is a freak event. If that's true, if abiogenesis is ultra-rare, then the picture of a galaxy full of habitable worlds changes completely. You can have billions of planets in the right temperature zone with oceans, with decent atmospheres, with all the basic conditions you think life needs, and most of them could still be completely sterile. No cells, no evolution, just chemistry that never quite crosses the line into biology. From far away, they'd look like good candidates, but on the surface, nothing ever wakes up. Now connect that to the search for intelligent life. If only 1 in a million or 1 in a billion habitable zone planets actually manages to spark life, then the base number you're starting with is already tiny. Out of all the worlds that could host biology, almost none do. And that's before you even ask whether that life becomes complex, builds big structures, or ever develops intelligence and technology. So the origin of life step might be the first major filter. You need a rare planet, in a rare stable configuration, and then you need a rare chemical accident, or a chain of accidents, to turn that planet from a rock with water into a world with cells. If that chain almost never completes, then most of the galaxy's habitable planets are just empty stages, with the lights on but no actors. In that scenario, your odds of having intelligent neighbours are not just low, they're close to zero. But even if we give you the optimistic version, even if we say fine, life starts fairly often whenever conditions are right. You still have another problem. Simple life is one thing, microbes are tough and efficient, they can fill a planet and stay there for billions of years. But the kind of life you're really interested in, the kind that can think, plan, build radios and rockets, That is a very specific outcome of evolution, and evolution is not aiming at that outcome at all. So the next question is even sharper. Even if the chemistry cooperates and biology begins, does evolution have some reason to push that life all the way up to intelligence like yours? Or is that step, the step from alive to aware and technological, another rare, fragile, low probability event? Earth is packed with life. Almost none of it builds radios. Look at your own planet for a second. Not as home, but as data. For more than 3.5 billion years, Earth has been full of living things, but for almost all of that time those living things were microbes, single cells, tiny, simple compared to you, but brutally effective at staying alive. They covered the oceans, they lived in rocks, they handled ice, heat, acid, salt, you name it. They did not need brains, tools, or language. From evolution's point of view, they were a massive success, and they did it without anything like intelligence as you usually mean it. That alone should make you pause. Life did not rush toward big bodies and big brains. It sat in the simple mode for most of Earth's history because simple worked. It took billions of years before complex multicellular organisms became common. Multicellular animals, the things you would recognize as animals in the usual sense, only show up in a serious way in the last roughly 600 million years. That is the last chunk of Earth's timeline, not the main story. Now zoom in even further. Those 600 million years are already just the last slice of the planet's age. Inside that slice, the kind of brain that can do long-term planning, language, tools, science, appears very late. Big, highly capable brains like those in humans are only a few million years old. Modern humans with language and culture are on the order of hundreds of thousands of years old. Industrial civilization, radio, electronics, the stuff that makes you detectable from space is maybe a century and a half old. On a 4.5 billion year timeline, that is a tiny, fragile spike at the end. So ask yourself, if evolution wanted intelligence, why did it wait so long? The answer is simple and harsh. Evolution does not want anything. There is no built-in arrow that points toward higher intelligence. There is no rule that says given enough time, every biosphere produces something like humans. Natural selection does one thing. It keeps traits that help survival in a given environment at a given time. If being smart helps, it might evolve. If being smart is a waste of energy, it will not. Look at the variety of life on Earth right now. You have whales, insects, fungi, trees, bacteria, archaea, algae, everything from deep sea to high atmosphere. Out of all of that, only one species runs around building radios, satellites, and telescopes. That is not for lack of opportunity. There are plenty of complex animals with decent brains and social behavior. Octopuses and other cephalopods can solve puzzles, use tools, and show individual personalities. Corvids, like crows and ravens, can plan, recognize faces, even make simple tools. Dolphins and some other marine mammals have complex communication and social structures. Some primates show culture and learning across generations. In other words, multiple branches of the tree of life have tried out higher intelligence to some degree. They got partway there, and yet only one line, your line, went all the way to a global technological civilization. Not because the others were too dumb in some absolute sense, but because their environments, their bodies, their histories did not push them across that particular threshold. Different pressures, different solutions. Now think about the cost of intelligence. Brains use a lot of energy. A human brain is only a small fraction of your body's mass, but it burns a large chunk of your daily calories. That is expensive. To support that, you need steady food. You need a body that can deliver enough energy to keep the brain running. You also need enough safety for complex thinking to actually matter. If you are constantly on the edge of starvation or constantly being hunted, a huge brain that spends time on abstraction and planning may not pay off. A simpler nervous system that does fast reflexes might be better. This is why intelligence is not a default outcome. It is a very specific solution to a very specific set of problems. On Earth, it took a particular environment, a particular climate history, particular accidents in evolution, for one line of primates to end up with language, culture, tools, and eventually technology. Change those conditions just a bit, and maybe dinosaurs never die out when they did, or maybe climate swings differently, or maybe another group rises instead, or maybe nobody ever crosses the threshold into building machines and studying physics. So even if life appears easily on many planets, and even if it evolves into multicellular forms in a lot of places, that does not mean those planets will generate technological species. Most of them probably will not. They might stay in a microbial Earth phase for billions of years, or they might get stuck at the level of simple animals and plants, with ecosystems that are rich and still, but have no species that cares about radio or astronomy. From a cosmic distance, those worlds would look alive, but you would not see laser beams or megastructures. Think again about your own timeline. Microbes dominate for over 3 billion years. Complex animals get a few hundred million. Large land animals get less. Technological humans get a blink. That tells you something about what evolution finds easy and what it finds hard. It finds stay simple and robust easy. It finds build fragile, energy-hungry brains that can imagine galaxies and invent radio hard. There is no guarantee other planets will hit the same rare combination of steps. And here is the real punch. When people talk about intelligent life in the universe, they often imagine something very close to you, a species that can understand math, build instruments, send messages, think about deep time. But the more you look at biology on Earth, the more it looks like that kind of intelligence is a narrow peak in a huge mountain range of possibilities. Evolution is perfectly happy to fill up all the valleys and lower hills with life that never climbs that peak. So even under generous assumptions, even if microbial life is common, even if complex life appears pretty often given enough time, technological intelligence could still be extremely rare. Maybe 1 in a million biospheres ever produces a species that builds a global communication network. Maybe fewer. In that case, you would not need the galaxy to be empty for you to feel alone. It could be full of primitive life, full of forests and oceans and alien microbes, and you would still have nobody to talk to. From your point of view, that is the same as being alone. If there are only a handful of technological civilizations in a whole galaxy, separated by tens or hundreds of thousands of light years, with tiny overlapping lifetimes, your odds of ever detecting one, let alone talking to one, are effectively zero. Not because physics says no life allowed, but because evolution says intelligence is optional, and almost nobody ends up paying the cost to get it. But that raises an even sharper question, one that hits directly at your own existence. If technological intelligence is that rare, if the chain from planet formation to conscious tool-using life is made of low-probability steps, then what does it mean that you are here now, already past many of those steps? Does that imply you somehow rolled through a sequence of almost impossible events, a great filter that nearly nobody else survives, and you happen to be on the far side of it? Or is the real danger still in front of you? If you're here, either the universe is friendly to intelligence, or you've already survived a nearly impossible gauntlet. This is the core of the great filter idea. Take everything we've talked about so far and put it in order. You need the right kind of star, not too big, not too small, long-lived and stable. You need the right kind of planet, rocky, in a safe orbit, with the right chemistry and a long-term energy supply. You need abiogenesis, that jump from non-living chemistry to the first self-replicating life. You need those first simple cells to become complex cells with internal structures. You need multicellular life. You need some of that life to develop tool use, social learning and language. Then you need that line to actually build a technological civilization. At any one of those stages, the probability might be very low. Maybe most stars are wrong. Maybe most planets lose their atmospheres. Maybe abiogenesis almost never works. Maybe complex cells are nearly impossible. Maybe multicellular life usually gets wiped out before it spreads. Maybe tool use never goes past clever animal on most worlds. If even one of those steps is extremely unlikely, it acts as a filter, stopping almost everyone from getting where you are now. Now look at Earth and notice how many strange things had to happen here. One of the biggest is the jump from simple cells, prokaryotes, to complex cells, eukaryotes. Your cells have a nucleus, they have mitochondria, they have internal compartments that handle different jobs. The leading idea for how that happened is endosymbiosis. At some point, a primitive cell swallowed another cell, and instead of digesting it, they formed a stable partnership. The swallowed cell became the ancestor of mitochondria, the power generators inside your cells. That is not a small tweak. That is a major structural change in how life is built. And as far as we can tell, it only happened once. All complex life on Earth, plants, animals, fungi, traces back to that single event. If that's true, then that engulfing and cooperating step was incredibly rare. Life lived as simple cells for billions of years without doing that. Then once it did, the door to complex bodies opened. If most worlds never get that event, they never get anything like you. Then look at oxygen. Photosynthetic microbes started pumping oxygen into Earth's atmosphere a very long time ago. At first, that oxygen reacted with rocks and the oceans. Only after hundreds of millions of years did it start to build up in the air. Eventually you get an oxygen-rich atmosphere, which is great for high-energy metabolisms like yours. But even then, complex animals did not explode immediately. For a long time, not much seems to happen. Then suddenly, in geological terms, you get a burst of new forms, the Cambrian explosion and everything that follows. That pattern, long stretches where the conditions look good enough, but nothing dramatic happens, and then a rapid burst of innovation tells you that evolution is full of contingencies. It is not smooth. It is not guaranteed. It depends on chains of events, sometimes triggered by climate changes, asteroid impacts, continental shifts, random mutations. Change the timing of those events or remove one of them, and the whole later history could look completely different. Maybe no large land animals, maybe no prime mates, maybe no you. So you have a ladder with many rungs, and some of those rungs might be extremely weak. Earth somehow climbed all of them, but that does not mean most planets do. The Great Filter hypothesis says, somewhere in that chain, there is a step that is so hard it almost never succeeds. Because you are here, you know that Earth passed it. What you don't know is whether that step was before you or still ahead of you. Here's where the anthropic trap comes in. You can only make observations from a planet where the whole chain worked. That means your sample is automatically biased. Of course, you look around and see a world where everything lined up just right, because if it hadn't, there would be no observer to notice anything. You cannot see all the dead worlds where the chain broke early, where life never started, or never got past microbes, or never produced intelligence. They are silent, they don't send data, and that makes it very easy to fool yourself. You look at Earth, you see life starting relatively early, you see complex cells, multicellular organisms, intelligence, technology, and you think, maybe this is normal. But that is like only interviewing lottery winners and then deciding winning must be common. You are a lottery winner by definition. You're only able to ask the question because your planet already beat the odds. That hides how brutal the odds might actually be. So consider one scenario. The Great Filter is mostly behind you. The rare steps are things like abiogenesis, the origin of complex cells, the jump to multicellularity, the path to large brains. Those steps almost never happen. Most habitable planets never get life. Most that get life never get complex cells. Most that get complex cells never get animals. Most that get animals never get intelligence. You live on one of the tiny fraction that made it through every stage. If that is the case, then the galaxy can be full of stars and planets and even simple life, and still have almost no technological civilizations at all. Maybe you are one of a handful, or even the only one, in the entire Milky Way at this moment in time. Not because the universe hates life, but because each step in the chain multiplies the unlikelihood. By the time you stack them all, the final result is almost zero. That would explain the silence very neatly. You do not hear anyone, not because you are not listening hard enough, not because of some conspiracy, but because statistically, there just is almost nobody to hear. You're in an empty room, built inside a huge building, inside an enormous city, but almost no one else ever found the door into that room. If that's true, your search for peers is basically doomed. You can build better telescopes, you can scan more stars, you can keep listening for centuries, and you will still probably hear nothing because there is nothing there to hear. The Great Filter did its work long ago, and you are one of the rare survivors. That sounds flattering at first, you beat the impossible odds, you rolled the cosmic nat 20. But the more you think about it, the more disturbing it becomes. Because if all the really hard steps are in the past, if most of the danger is already behind you, then the silence out there is a mirror, showing you what almost always happens instead of you. But there is another possibility, one that is even more disturbing. What if the steps behind you are not the hard part? What if the truly deadly filter is not in your past but in your future, waiting for every technological civilization that reaches your level and almost always wiping them out before they have time to spread or to be heard? Maybe it's not that you can't find them, it's that they all kill themselves before you ever get the chance. Think about the timescales you're dealing with. A rocky planet in the habitable zone, with a decent atmosphere and a stable orbit, can stay friendly to life for billions of years. Earth has had conditions that support liquid water for most of its 4.5 billion year history. Stars like the Sun can burn steadily for around 10 billion years. That's a long, wide window. Now compare that to the lifetime of a technological civilization at your level. Not microbes, not simple animals, but a species that can reshape its planet, tap huge energy sources, and build global communication networks. How long has that phase lasted on Earth so far? A few hundred years at most. The industrial era, the fossil fuel era, the we can alter the entire atmosphere era is less than 3 centuries old. Radio, spaceflight, nukes, digital networks, all of that fits inside a tiny slice of time. So you have this mismatch. Planets can stay habitable for billions of years, but the radio-bright, tool-heavy, dangerous but powerful phase might last for only a few centuries before something breaks. If that is typical, then most technological civilizations may burn fast and die young. That alone would make it very hard to catch one in the act. Now ask what actually changes when a species like yours reaches that level. You go from being limited by local energy, like muscle, wood, maybe simple wind and water, to tapping dense, stored energy like fossil fuels, nuclear reactions, and maybe one day, advanced AI-controlled systems and other high-risk tech. You suddenly have planet-scale power, but your brains, your instincts, your social wiring are still built on primate hardware, tuned for small groups and short-term survival. That combination is unstable by default. You get tools that can alter the entire climate, tools that can poison oceans, tools that can wipe cities off the map in minutes, tools that can copy themselves in software and act faster than you can think. You do not suddenly become wise just because your technology jumps. You carry all the same biases, fears, tribal instincts, and short-term thinking into a world where your mistakes can have global consequences. You can already see the edge of this in your own data. Look at Earth's CO2 levels and temperature curves over the last few hundred years. For millions of years, the climate has swung up and down, but slowly, driven by natural cycles. Then, in about 2 centuries of industrial activity, you push greenhouse gas levels higher than anything your civilization has seen before, and you start moving global temperature on a timescale of decades, not geological ages. From a planetary point of view, that is a violent shove. You're destabilizing systems that took millions of years to settle. Ice sheets, ocean circulation, weather patterns, ecosystems, all are being forced to adapt faster than many of them can. You did this without planning it, just as a side effect of chasing growth and energy the easiest way you knew how. That's what planet-scale power with primate-scale brains really looks like. And climate is just one threat. You also built nuclear weapons, devices that can level cities and potentially trigger large-scale war that would wreck your infrastructure and food systems. You're developing advanced AI and autonomous systems that could, if mishandled, make critical decisions faster than humans can control, or magnify bad incentives across the whole planet. You have biological tools that could, in principle, create engineered pathogens. Each of these is a lever that can move the entire civilization, for good or for collapse. So imagine this is not unique to you. Imagine every technological civilization, anywhere in the galaxy, goes through a similar phase. They discover high-density energy. They industrialize. They build weapons with global reach. They meddle with their own environment and with self-replicating systems. They have old brains running new tech. How many of them navigate that minefield without blowing themselves up or grinding their societies into something that can no longer support a high-tech infrastructure? If the answer is almost none, then you don't need a great filter in the deep past, you have one waiting in the future. Civilizations light up the radio spectrum for a short period, maybe a few hundred or a few thousand years. Then either they collapse back to a pre-industrial level, or they go extinct. Their cities crumble, their satellites fall, their signals fade. On cosmic timescales, that little flash is over in an instant. Now think about what that would look like from far away. You might have a galaxy where technological civilizations are not ultra-rare in time. They pop up regularly over billions of years, but each one is brief and self-destructive. By the time another civilization comes along with the right tools to listen, all that's left from the previous ones are faint fossilized traces, maybe some unusual chemistry on a planet, maybe some debris in orbit that has already decayed, maybe nothing at all. From your perspective, that galaxy would still look empty. The odds that you and another civilization are in your brief broadcast and survive window at the same time, and close enough for detection, are tiny. Most of the time, you'd be looking at silent graveyards, worlds that once had cities and networks and noise, and now are quiet again. You would not see a thriving interstellar community. You would see isolated, short-lived flares that almost never overlap. This is a very different kind of great filter from the "we already passed the hard step" story, but it explains the silence just as well. If the filter is mostly ahead, in the form of self-destruction, mismanaged technology, or slow environmental collapse, then intelligent life might be fairly common in the galaxy, in the sense that it appears again and again over time. It just almost never lasts long enough or spreads far enough to become easy to notice. So you are stuck between two disturbing options. Either the universe was brutal in the past and almost nobody made it to your level, or the universe is brutal in the future and almost nobody survives your level. In both cases, the outcome for your search is the same: you listen and you hear nothing. And even if somehow some civilizations do manage to thread that needle to survive their own power and stay stable for millions of years, they still have to fight another enemy, one that does not care about intelligence or wisdom. Even if they live, their signals still have to cross the void, and the void is not kind to fragile messages. Even if aliens are out there, physics is doing everything it can to erase their messages before you ever hear them. Start with the most basic problem. When you send out a signal and it spreads in all directions, its power gets diluted fast. Imagine the signal spreading out as a growing sphere. Every second that sphere gets bigger, and the same total energy is now spread over a larger surface. The important part is this: when you double the distance from the source, the signal strength at your location is cut to a quarter. If you go 10 times farther, it is down to 1/100th, pushed to 1,000 times farther, and you're down to a tiny fraction again. The drop is brutal. Now plug in real numbers. Your casual broadcasts like TV, radio, airport radar are not aimed at specific stars, they just leak out. They are strong near Earth, but after a few light years they sink into the background. At hundreds or thousands of light years, that leakage is gone as a usable signal. It is not that it literally disappears, the waves are still there, but the strength at any given spot is so low compared to natural noise that even your best detectors would not be able to pull it out. So if another civilization is doing what you did in the 20th century, spraying radio in all directions without thinking about deep space, you should not expect to hear that from across the galaxy. Physics will kill it for you just by spreading it thin. The only way to get around that is to focus, to stop broadcasting like a floodlight and start using tight beams aimed at specific targets, or at least narrow cones. But once you do that, you introduce a new problem. Now the signal is strong where it hits, but it misses almost everything else. If you're not in the beam, you hear nothing. On top of that raw spreading loss, the signal has to pass through the stuff between the stars, and that stuff is not perfectly transparent. The space between stars is filled with very low density gas, dust, and free electrons. Over large distances, this material has real effects. Radio pulses get dispersed, lower frequencies get delayed more than higher ones, the pulses stretch out and smear. Some frequencies get scattered or absorbed more than others. Over thousands of light years, that can distort a clean, sharp signal into something that looks fuzzy and weak. That means that even if an alien transmitter starts clean, by the time its signal reaches you, the shape of the pulse, the spacing of the bits, the neat structure you might expect can be altered. Your detection software often assumes certain neat, narrow patterns, because those are easier to search for. But the universe does not care about that. It distorts things in ways that can make an artificial signal look more like a messy, natural process, unless you know exactly what to look for. Now, add encoding and bandwidth choices on their side. You tend to imagine old-style broadcasts, simple carriers, narrowband tones, maybe basic modulation schemes. Why? Because those are the kinds of signals you know how to find quickly. You train your algorithms to look for narrow, persistent spikes in frequency, because nature rarely makes those. That is the classic SETI target, a monochromatic tone sitting in a quiet part of the spectrum, turning on and off in a detectable way. But what if advanced civilizations don't talk like that? You're already moving away from that style yourself. Your own communications are shifting toward fiber optics, low power, directional microwave links, spread spectrum signals that deliberately look like noise to avoid interference and eavesdropping, highly compressed data streams that push information as close as possible to the theoretical limits. To an outside observer who doesn't know your protocols, a lot of that traffic just looks like random fluctuations in the noise floor. Take that trend and extend it by 1,000 years, or 10,000. A far older civilization might use ultra-narrow laser beams in optical or infrared light, so tight that they only hit a very small target region. They might use frequencies you barely monitor. They might use neutrinos or gravitational waves or other channels you don't even have the technology to detect well. And their data formats might be maximally compressed, encrypted, or encoded in ways that look statistically identical to thermal noise, unless you know the key or the exact pattern. From your perspective, even if one of those beams sweeps across Earth, your instruments could log it and throw it away as background variation, because it does not match your limited templates of what a signal should look like. You would not see a neat hello, you would see a slightly odd spike or a short burst hidden in the noise, and unless you are specifically searching for that kind of thing across massive data volumes, you never notice it. Here's the uncomfortable part. Most of your listening strategy still assumes aliens are basically stuck in your past. You look for strong, continuous radio beacons or simple tones because that is what you would build if you wanted to be noticed with 20th century technology. But your own societies are already abandoning loud, wasteful broadcasting. Old-style TV and radio towers are shutting down or shrinking. Communication is moving into cables, tight satellite beams, and low-power local networks. To a distant listener, Earth is already becoming radio quieter than it used to be, so you have a paradox built into your search. You are most sensitive to civilizations that use crude, wasteful technology you already consider outdated. The more advanced and efficient they become, the harder they are to detect with methods designed for simple, obvious signals. And at the same time, physics is weakening and distorting everything over large distances, and you're only scanning narrow bands of frequencies and regions of sky at any given time. Put it all together. There could be real alien signals crossing your part of the galaxy right now, some from civilizations a bit like you, some from societies far beyond you. Some might be weak, some might be tightly focused, some might be wrapped in complex encoding. Between the inverse square drop in strength, the smearing and scattering in the interstellar medium, your limited coverage, and your human assumptions about what obvious looks like, Those signals could be sliding straight through your data, tagged as noise, never getting a second look. So when you say, "Oh, we've heard nothing, so maybe there is nothing to hear," you are stacking the deck in favour of a very particular picture of communication, and ignoring how many ways physics and technology can hide real signals. The silence may not mean absence. It may just mean that your ears and your expectations are badly mismatched to what is actually out there. But even if you fix that, even if you build better detectors, search more of the spectrum, scan more of the sky and use smarter algorithms, you still run into another brutal limit. All of this listening only matters if someone else is talking at the same time you are listening, and close enough that their signal can reach you before both of you change or disappear. And when you line up the lifetimes of planets, stars, and civilizations, you realize something unnerving. The galaxy may be full of brief flashes of intelligence, all separated in time and distance so badly that almost none of them ever overlap. The galaxy could be full of civilizations. You and they might simply never share the same office hours. Think about the Milky Way as a system that lives for around 10 billion years in its current disk form. Now drop technological civilizations into that timeline, but make each one short-lived on that scale. Be generous and say a high-tech phase lasts 1,000,000 years, which is already far longer than you've managed so far. 1,000,000 years sounds huge to you, but compared to 10 billion, it's just one part in 10,000. Now imagine sprinkling those civilization flares randomly through the galaxy's history. One sparks to life 8 billion years ago, shines for 1,000,000 years, and then disappears or goes quiet. Another appears 3 billion years ago, another only kicks off 500 million years ago. Most of them are not only separated in space, but also in time. The chance that two of them are both on in the same era and close enough to talk is small by default. And remember, it is not enough that they overlap at all. Their peak high-energy communicative phases have to overlap, and they have to be within a distance where signals are still detectable. If one civilization hits its stride near the outer edge of the galaxy, and another blooms toward the inner regions, the distance between them could be tens of thousands of light years. At that range, even deliberate focus signals become hard to notice, and if one flickers out before the other gets advanced enough to listen, their windows never meet. This is where the Drake equation is useful, not as a precise calculator, but as a timing argument. It takes factors like star formation rate, fraction of stars with planets, fraction of those with habitable worlds, fraction where life starts, fraction where intelligence appears, fraction that developed technology, and the average lifetime of a detectable civilization. When people plug optimistic numbers into it, they sometimes get results like maybe there are a few, maybe a few dozen, maybe a few thousand civilizations in the galaxy over its whole history. But when you then spread those civilizations out across a disk 100,000 light years wide and 10 billion years long, the average separation in space and time is huge. The typical distance between neighbours might be thousands of light years. Their radio loud periods might barely overlap. Even if the absolute count of civilizations over all time is respectable, the number that are active and close enough to be seen at the same moment can easily drop to something like 1 or 0. Star formation history makes this even more uncomfortable. The Milky Way did not produce stars at a constant rate. There was a cosmic noon in the past, a period where star formation was much higher than it is now. Many planetary systems are older than the Sun by billions of years. That means whatever could happen on Earth could have happened elsewhere long before your planet even formed. Imagine a world that formed around an older star, had a stable habitable period, grew life, climbed through all the hard steps, reached intelligence, built technology, and then burned out or collapsed 2 or 3 billion years ago. At that time, Earth might have been a world of microbes, with no oxygen-rich atmosphere yet, no plants on land, no animals. Any signals that civilization sent would have passed through this region of space long before anybody here had ears to listen or receivers to detect them. From your point of view, those civilizations are gone in every practical sense. Their light, their radio, their artifacts are either too far away, too faint, or too old to be noticed. They had their peak, and it ended long before your story began. You're late to the party, not in a moral sense, just in a scheduling sense. You showed up after most of the interesting conversations were already over. Now flip the perspective to humanity. You have been radio bright for about 100 years. That's the length of time your signals have had to travel outward as the detectable shell. 100 light years is nothing compared to the size of the galaxy. And that 100 years is a tiny slice of Earth's age, about 1/10 millionth. For 4.5 billion years, this planet did not announce itself in any way a distant observer could easily detect. For 4.4999999 billion of those years, there was no radio noise, no satellites, no strong technosignatures. You've also only been listening carefully for a few decades, and even then, only in specific bands, at specific times, towards specific targets. So effectively, you just walked into a room where a complicated 24/7 conversation has been going on for billions of years. You listened for a moment, in one direction, and heard nothing. That does not mean the room was always silent. It might just mean no one happened to be speaking loudly, in your language, right when you finally bothered to pay attention. Put all this together, and the bottom line is harsh. You're checking your cosmic phone once in your entire lifetime as a species so far, hoping to catch a notification that flashes for a tiny instant on galactic timescales. Unless civilizations are both very common and very long-lived, the odds that your brief listening window overlaps with someone else's brief broadcast window are just not good. And that is before you account for distance-weakening signals, for interference in the interstellar medium, for differences in technology, and for your narrow search strategy. Even if you live in a galaxy where intelligence emerges fairly often, most of those minds are separated from you by such huge spans of time and space that you will never know they existed. From your vantage point, the sky looks empty, even if the galaxy's history is full of activity. So the scheduling problem is not some minor technical detail. It is a fundamental reason the universe can be both full of life over time and empty right now from your point of view. You are one flare in a dark ancient sphere, and most of the other flares have already risen and faded, or have not yet ignited. But there is another layer that makes all of this even worse. It is not just timing and distance that fight you. The galaxy itself is not a calm, safe environment. It is full of radiation, explosions, gravitational chaos, and long-term hazards that can wipe out complex life before it ever has a chance to reach the point you are at now. Space isn't just big, it's hostile, and it may wipe out complex life before it ever has a chance to get clever. When you think about habitability, you probably picture distance from a star, temperature, oceans, atmosphere. But zoom out one more level. A planet doesn't just sit next to its star. It sits inside a galaxy full of violent events. Massive stars live fast and die hard. When they run out of fuel, they can explode as supernovae, throwing out huge amounts of high-energy radiation and charged particles. Even worse, in some rare cases, collapsing stars can produce gamma-ray bursts, tight beams of extremely intense gamma radiation that can travel for thousands of light years. If one of those events happens close enough to a planet with life, it's bad news. Intense radiation can strip away parts of the atmosphere, especially the protective ozone layer. That lets more harmful ultraviolet light from the parent star reach the surface. It can change atmospheric chemistry, damage DNA, and trigger mass extinctions. You don't need a direct death ray to kill a biosphere. You just need enough radiation to quietly wreck the shield that keeps a surface comfortable. That means some parts of a galaxy are simply more dangerous than the others. This is where the idea of a galactic habitable zone comes in. Too close to the galactic center, and you have high star density, more massive stars that go supernova, more black holes, more radiation, and more gravitational disturbances as stars pass close to each other. Planets there might form, but they live in a shooting gallery, constantly at risk of being blasted or having their orbits disturbed. Move too far out toward the edge of the galaxy, and you hit a different problem. There, star formation has been weaker, and the gas is poorer in metals. In astronomy, that means all elements heavier than helium. Those heavy elements are what you need to build rocky planets, complex molecules, and eventually biology as you know it. In the outer regions, you might have fewer solid planets to begin with, and the chemistry needed for life could be limited. So there's a rough sweet spot in distance from the galactic centre, where you have enough heavy elements to build Earth-like worlds, but not so much chaos and radiation that you constantly sterilise them. Even inside that zone, there are better and worse neighbourhoods, depending on local star types, cluster density, and past events. Your own position, out in a relatively calm spiral arm, away from the central chaos but not in the metal-poor outskirts, looks suspiciously lucky. Now step back in time. The early universe was worse in almost every way that matters for complex life. At first, it had almost no heavy elements at all. The first generations of stars were huge and short-lived. They burned bright, then exploded violently, filling space with radiation and shockwaves. Star formation rates were high, and with that came frequent supernovae and probably more gamma-ray bursts. Only after many cycles of star birth and death did the universe enrich itself with enough heavy elements to build lots of rocky planets, and only after the most intense period of violent events calmed down did long-term stability become more likely. That means there may have been billions of years where the universe simply wasn't a good place for complex surface life to last. Early planets might have had oceans and atmospheres, but they lived under constant threat from nearby explosions. Any attempt by evolution to climb toward complexity could have been reset again and again. Even now, the Milky Way is not some fixed frozen structure. Data from missions like Gaia show that the galaxy is rippling, warped, and still reacting to past collisions with smaller galaxies. Stellar streams, waves in the disk, and other structures tell you that orbits are not perfectly stable over billions of years. Whole regions can be slowly shaken as gravity tugs stars around, changing their paths, altering how often they pass through dense regions, gas clouds, or spiral arms. Every time a star's orbit shifts, its planets go along for the ride. Over hundreds of millions of years, that can move a system into regions with higher radiation, more nearby supernovae, or more encounters with giant molecular clouds that can disturb comet reservoirs. That might trigger impacts, climate shifts, or slow atmospheric loss. None of these events have to be perfectly lethal to be a problem. If they hit at the wrong time, they can knock a planet out of a delicate, stable state just as life is trying to get ambitious. So when you imagine a habitable planet, don't just picture a blue sphere circling the calm star forever. Picture a target under slow, random fire from the rest of the galaxy. Sometimes the hits are small, just enough to shake ecosystems. Sometimes they are big enough to reset the whole experiment. Given enough time, some planets will sail through with only minor damage. Others will get unlucky early and often. Now, connect this to intelligent life. To get to something like you don't just need life. You need billions of years where life can survive, adapt and climb through many stages of complexity without being knocked all the way back to zero. You need long periods with no total sterilization, no full atmospheric loss, no permanent snowball state, no runaway greenhouse that melts everything, no series of impacts that keep resetting evolution before it can get past microbes and simple animals. Large parts of the galaxy may simply not allow that kind of long, quiet run. Close to the centre, the chance of a planet getting hit by intense radiation or a nearby explosion is higher. In crowded regions, gravitational encounters can destabilize orbits. In regions shaped by recent mergers or strong perturbations, stars and their planets might be moving through more dangerous environments. These are not bad places where you'd expect a fragile, tool-using intelligence to have billions of years of relatively stable conditions to evolve and then build technology. From that perspective, the Milky Way is not a uniform playground. It is more like a patchy map of safe and unsafe zones. Some regions might be almost completely off-limits for the long-term evolution of intelligence. Others might allow simple life, but punish any attempt to build complex ecosystems with repeated shocks. Only a subset of distances from the centre and a subset of orbital paths give you something like Earth's long, mostly stable history. That immediately cuts down the number of places where intelligent life can even try to appear. before you worry about origins of life, evolution, or self-destruction. And remember, you only see your own lucky case sitting in a relatively calm arm, in a relatively quiet era. You don't see the planets that got hammered early, lost their atmospheres, and never recovered. So add this to the growing list. The universe is big, but much of that volume is either too poor in heavy elements, too chaotic, or too unstable for complex, long-lived civilizations. The good neighborhoods are limited. Inside those, you still have to get rare chemistry, rare biological steps, and rare survival through your own technological adolescence. And even if a few civilizations do manage that, even if they find themselves in the safe pockets, survive the violence, and reach a point where they could reveal themselves, there's another twist. In a galaxy this dangerous and unpredictable, broadcasting your existence might not just be risky, it might be the stupidest possible move. What if the reason you don't hear anyone is not just that it's hard, but that any species smart enough to last decides that being loud is a good way to die? What if you can't find them because anyone loud enough to be found doesn't stay alive for long? Imagine you're a young civilization in a universe where you don't know who else is out there. You don't know their motives, their ethics, their level of technology, or how they react to threats. You just know this. Physics allows you to see things very far away, and it also allows someone far away to see you. In that situation, shouting your exact location into the dark is not a neutral act. It is a strategic move, and maybe a very bad one. This is the core of the dark forest idea, but you don't need philosophy to get it. You only need basic game theory. If you know nothing about other players, and you know that some fraction of them could be dangerous, rational, or even just paranoid, then broadcasting "here we are, here's our star, here's what we're made of, here's how our technology works" could be a mistake you don't get to repeat. Silence, or at least caution, becomes the safe default. Now flip it around. Imagine you are the older, more advanced civilization. You pick up a signal from a new, loud species, clearly using radio, clearly broadcasting without much thought about security. You don't know if they will stay friendly as they grow in power. You don't know if they will learn to send self-replicating probes or build weapons you can't defend against. The safest move in a cold, unknown universe might be to prevent that risk early before they can threaten you. That logic is ugly, but it's simple, and you don't have to assume evil aliens, you just have to assume very cautious ones. If that's the background rule, then the winning strategy is not to be loud and open forever, is to be quiet, controlled, and hard to notice. A civilization that learns this lesson early will deliberately shrink its footprint. It will minimize radio leakage, using fiber, cables, and highly directional links instead of big, wasteful broadcast towers. It will use tight beams for long-distance communication with just enough power to reach the intended receiver, and nothing extra. It will run its energy use in ways that blend into natural backgrounds, dumping waste heat in wavelengths and patterns that look like normal astrophysical processes. From the outside, that kind of civilization would not look like a giant glowing beacon. It would look like a slightly unusual star or a slightly odd infrared source or nothing special at all. Its communication traffic would either miss you entirely because the beams don't cross Earth, or if they do, they would look like brief, narrow events lost in your noise. To you, the sky would still look quiet, not because no one is talking, but because they are talking in ways that are intentionally hard for strangers to detect. Here's the uncomfortable part. You're already starting to act this way yourselves. There is an active argument on Earth about active SETI, sending deliberate, powerful messages to nearby stars that say, "We are here, this is us." Some scientists think it's a good idea, some think it's neutral, and some are strongly against it. Their reasoning is basically the dark forest logic. You don't know who will hear you, you don't know what they'll do with that information, and you can't take it back once it's out. The fact that this debate exists at all is important. It shows that even a young civilization like yours, with very limited experience, can already see the risk in shouting into an unknown environment. Any species that understands basic risk management will at least consider the option of staying quiet. And the more advanced they are, the more time they have had to think through worst-case scenarios, the more incentive they have to be careful. And remember, even without fear, efficiency pushes in the same direction. Loud, omnidirectional broadcasts waste energy. Tight beams and local networks are simply better for high-capacity communication. So you've got two forces pushing civilizations away from big beacon behavior, cold survival logic and basic engineering optimization. That combination makes long-term loudness unlikely. Now think about testing this. How would you know if everyone who survives chooses silence? You wouldn't. That's the whole point. If the only civilizations you can easily detect are the loud, naive, early-stage ones, and if those are either short-lived or get selected against, then the ones that remain, the ones that last millions of years, are exactly the ones that don't show up in simple SETI searches. From your vantage point, the galaxy would look exactly the way it looks now. No constant shouting, no obvious beacons, no giant "we're here" billboards. Just normal-looking stars, some strange objects that you explain as exotic but natural, and background noise. You could be surrounded by highly advanced societies that made a collective decision, each on their own, to treat visibility as a threat. There's no easy way to prove that, and no easy way to disprove it either. The observational result in both cases is the same: silence. This is what makes the dark forest idea so disturbing. It doesn't require evil, only caution. It doesn't require a secret alliance, only similar reasoning. And it doesn't leave you a simple experiment you can run to decide if it's true. If everyone who is loud dies out, and everyone who stays quiet survives, then after a few billion years, the only ones left are quiet. You arrive late, turn on your receivers, and you hear what you'd expect in that universe: almost nothing. So the absence of loud signals, by itself, doesn't point clearly toward "we are alone." It may be exactly what you'd expect from a galaxy full of very cautious minds, all independently deciding that broadcasting is a threat. If that is reality, then your current SETI strategy, waiting for someone to be sloppy or generous enough to shout, is not just optimistic, it is fundamentally mismatched to the way long-lived civilizations behave. But even if you set aside the dark forest logic, even if you assume there's no great predator out there, and that everyone is friendly or indifferent, you still face another almost embarrassing problem. Right now, you're trying to read the entire universe through instruments that, on the cosmic scale, are tiny. Your best telescopes, your biggest dishes, your flagship observatories are still extremely limited compared to the size and complexity of what you're trying to scan. You're walking into this supposed dark forest not with night vision and a full map, but with a narrow flashlight that only shows a small patch at a time. And then you are surprised you don't see much. You're trying to read the universe through a pinhole and then wondering why you don't see anything interesting. Start with what your best instruments actually do. Even with giants like JWST, you almost never see an exoplanet as a little disk, with continents and clouds. Most of the time, you only know a planet is there because its star gets a tiny bit dimmer on a regular schedule. The planet passes in front, blocks a small fraction of the light, and your detectors notice that dip. From that, plus some extra measurements, you infer size, orbit, maybe some rough clues about the atmosphere. That's the level you're at. You're inferring entire worlds from a 1 or 2% change in a star's brightness, or from a tiny wobble in the star's motion. You're not resolving cities, or continents, or artificial structures. You're barely resolving the planet itself. At that level, any talk about seeing alien megacities, or spotting alien solar panels, or normal exoplanets is pure fantasy. The data you get is just too coarse. The hard limit underneath this is simple. Resolution gets worse with distance, unless your telescope gets much, much bigger. To separate a planet from its star as two distinct points of light, you need huge angular resolution, and the farther away the system is, the harder that gets. Right now, for most stars that are tens or hundreds of light years away, the star is just a point, and any planet next to it is buried inside that point, completely drowned in the glare. So ask a blunt question. if a civilization covered its whole planet in solar collectors or built a ring of structures in orbit, would you see it? In almost every case, no. At the distances where most of your exoplanet targets live, even a planet-wide megastructure would change the light from the star by such a tiny amount, in such subtle ways, that it would be at or below your current detection limits. Unless they built something truly extreme on the scale of the whole star, you would not see a clear, sharp, "this is artificial" signature. And even then, it's not enough for an effect to exist. You have to actually look at the right star in the right way, with the right instrument. Telescope time is limited. You cannot stare at every star all the time, so you make choices. You point your best hardware at bright, nearby, and scientifically interesting targets, because those give you the cleanest data and the highest chance of publishable results. That creates another bias. A civilization on a faint red dwarf 2,000 light-years away is simply not on your list. You are not staring at that star with JWST for hundreds of hours. You are not doing repeated, high-precision spectroscopic passes looking for weird gases or strange flickers. It's invisible to you in a practical sense, because your resources are focused somewhere else. Even within your own neighbourhood, you're selective. There are millions of stars within a few thousand light-years. You've only checked a small fraction of them with serious detail. Most have not been monitored continuously, across many wavelengths, at high sensitivity. If a distant planet went into some massive engineering phase 1,000 years ago, or 10,000 years ago, your current survey coverage would almost certainly have missed it. You might say, okay, but new telescopes are coming, so this problem will go away. Missions like the Roman Space Telescope and the huge ground-based extremely large telescopes will absolutely help. They will measure more exoplanets in more detail. They will let you see weaker signals and maybe take crude images of a small number of nearby worlds. That is real progress. But look at the scale again. These observatories will still only be able to target specific slices of the sky, at specific times, in specific bands. They do not magically turn the whole sky into a high-resolution movie. They give you a better pinhole, not a full window. The number of stars you can study deeply, with full spectra and repeated observations, will still be tiny compared to the total number of stars in the galaxy. On top of that, every instrument has a favourite wavelength range, a sweet spot. JWST is powerful in the infrared. Other telescopes focus on visible, ultraviolet or radio. No single facility watches everything, from low-frequency radio all the way up to high-energy gamma rays, with equal sensitivity all the time. So even if an alien technosignature exists, it might live in a range that you are not monitoring carefully, or at times when you're pointed somewhere else. This is why it's wrong to think of your instruments as almost good enough. Just a bit more and we'll see aliens. In many ways, they're not even close. You're trying to spot tiny anomalies on faint points of light from across vast distances, using tools that were mostly designed for general astrophysics, not for hunting deliberately hidden technology. You are basically blind to anything that is not screaming, "Look at me," in a way that matches your narrow assumptions. And remember the earlier points. If advanced civilizations try not to be obvious, they will avoid exactly the kinds of big, wasteful, easy-to-spot signals you are best at catching. They will not run giant omnidirectional radio beacons. They will not dump waste heat in nice, clean, obvious patterns if they can help it. They will bury their activity under natural-looking emissions or inside frequency ranges and modulation schemes that your current surveys barely touch. So you are in a double bind. Your telescopes are too limited to see anything but the closest, loudest, or strangest cases, and the civilizations most likely to survive long-term are also the ones that have the strongest reasons to avoid being close, loud, or strange in your eyes. That's not just a technical gap. It's a structural mismatch between how you look and how they would behave. In practice, this means that even if a nearby star hosted a planet with massive planet-scale engineering, you might not notice it unless you happen to study that exact system in detail, at the right wavelengths, for a long time and knew exactly what to look for. And for most stars, that kind of deep, dedicated attention is simply not happening. So when someone says, "We've pointed our best telescopes at the sky and seen no obvious alien structures," the honest translation should be, "We've taken a quick peek at a few promising targets with tools that can barely separate planets from their stars, and we've seen nothing that's both huge and simple enough to stand out." That's not nothing, but it is nowhere near a full survey. Your instruments aren't just not good enough yet, they are so limited in coverage and resolution and wavelength that you're effectively blind to any but the loudest, closest, weirdest civilizations, and those might be exactly the kinds that physics and survival pressure select against. But even if you upgrade the hardware, even if you somehow got a perfect view of every planet around every nearby star, there's another problem waiting. You're still assuming that alien technology will look like technology to you. You're assuming it will line up with your idea of antennas, transmitters, factories, and lights. What if it doesn't? What if advanced civilizations move into forms of communication and engineering that, from your point of view, are indistinguishable from normal physics or from a quiet natural planet? If that's the case, then it's not just your telescopes that are acting like blinkers, it's your entire idea of what you're trying to see. You're not just looking in the wrong place, you might be looking for the wrong thing. Right now, most people still instinctively picture alien signals as radio messages, like some cosmic version of old Earth broadcasts. But radio, the way you've used it so far, is a phase, not a final stage. In just over a century, you've gone from huge, wasteful broadcast towers to tight satellite links, fibre optics under the oceans, and low-power, local networks. A lot of your high-value communication is now invisible from space, locked inside cables or narrow beams. Push that trend forward 1,000 years. If your civilization survives, keeps optimizing, and keeps worrying about interference and security, Earth from the outside could look almost radio silent. Most of your data would move through physical channels or through carefully shaped transmissions that barely leak. A SETI observer looking for 1960s-style broadcast noise would point a big dish at your star, listen, and hear almost nothing. They would conclude, "No one home," while billions of devices chat non-stop under the noise floor. Now, stretch your imagination to civilizations much older than you. Give them 1,000,000 years of technological development. There is no reason to think they are stuck using the same bands, the same particles, or the same simple encodings you like today. They might use channels you barely know how to detect at all, like neutrinos, which pass through almost everything and are hard to block. Or they might use subtle quantum effects, entangled systems, or engineered space-time ripples as part of their communication infrastructure. From your point of view, those channels are effectively invisible. You don't have the detectors, you don't have the bandwidth, and in many cases, you don't even have a clear theory that says, look here in this exact way. So if a 1,000,000-year-old civilization has moved its important traffic onto those kinds of systems, while leaving very little in boring old radio and visible light, you would see that as silence, not because they are quiet, but because their activity sits outside your current detection envelope. This is where the idea of technosignatures gets broader than radio signal from alien TV station. A technosignature is any detectable sign of technology or industry, not just a message. That could be atmospheric gases in weird ratios that scream machines are working here. It could be waste heat at levels and patterns that normal geology and biology struggle to produce. It could be artificial lighting on the night side of a planet, or regular unnatural changes in a star's brightness as structures pass in front of it. You're just starting to look for that kind of thing. Astronomers have begun scanning exoplanet atmospheres for industrial pollutants, like certain chlorofluorocarbons, that don't have a clear natural source. People are modelling what a planet covered in solar collectors might look like in infrared, or how city lights might show up in extremely precise light curves. So far, nothing definitive has turned up. But it's important to be honest, this survey phase is brand new and your sample size is tiny. You've barely begun to check a few worlds in any detail. On top of that, there's a nasty classification problem. Real data is messy, stars flicker, disks of dust and gas can dim them in irregular ways, magnetic activity can cause strange light curves, and instruments have their own quirks. When you see something odd, the safer assumption, especially in professional science, is we've got some weird astrophysics going on, not we found alien engineering. Take the idea of a Dyson swarm, a collection of structures around a star capturing a large fraction of its light. In principle, that could produce a distinctive signature, like a star that is dimmer in visible light but bright in infrared, because most of its light is being absorbed and re-radiated as heat. But dust can do something similar. Thick disks, debris, and clouds around stars can also block visible light and glow in infrared. Unless the pattern is extremely clear and extremely strange, the first label you stick on it is dusty system, not mega engineering project. Even in photometric surveys, when a star shows unusual dimming, like irregular drops in brightness, the first response is to hunt for natural explanations, disks, comets, instrument errors, stellar activity. That's good scientific practice. The problem is, if a real technological structure exists that looks even somewhat like a natural disk or cloud, it will get filed under odd but natural and left there. In other words, some technosignatures could already be in your catalogues, but tagged as weird star or complex disk instead of possible civilization. So you have two layers of blindness. One, advanced technology may operate in channels and forms you barely monitor or understand, which makes it literally invisible to you. Two, even when it does overlap with your instruments, it might look enough like natural processes that you don't recognize it as anything special. It just becomes part of the astrophysical noise you expect. Now add your own biases on top. You still tend to treat alien tech as something that should be obvious, dramatic, and almost cartoonish. Giant beacons, giant structures, simple repeating messages in familiar formats. You're comfortable with alien technology that looks like a scaled-up version of 20th century Earth, because that's what your intuition can handle. But the further you move away from that picture, the less likely you are to even label something as a candidate. Here's the core problem. If you only accept alien technology when it looks like a 1960s radio station, with a big carrier wave shouting hello in clear tones, you'll probably never find anything. Real civilizations, if they exist, are under pressure to be efficient, secure, and maybe quiet. Their tech will evolve away from broadcasting, away from waste, away from obviousness. From a distance, a planet full of advanced computing and engineering could look like a slightly warm, slightly odd, but still natural world. So when you put together your search strategy using narrowband radio scans and a few targeted technosignature ideas, you're not just limited by hardware, you're limited by imagination. You're mapping a tiny part of the space of possible technologies and then treating the empty parts of that tiny map as proof that the whole territory is empty. It's like tuning an old radio across one narrow band hearing static and deciding there are no networks, even while fibre optics and Wi-Fi are carrying almost everything around you. That leads to an uncomfortable conclusion. Even if the galaxy is full of technology, your current methods could easily miss almost all of it. You might be surrounded by quiet planets that are anything but simple, worlds where the surface looks normal, while the real action happens underground, in orbit, in engineered microenvironments, or in channels you don't know how to probe. From where you stand now, all of that collapses into one word: silence. But there's one more twist. And it doesn't come from technology. It comes from time. It's possible that the universe is actually very good at making habitable planets, very good at making life, and maybe even decent at making intelligence, but still looks empty to you for a simpler reason. Your species might have shown up early in the story. Most of the civilizations that will ever exist might just not have had time to appear yet. What if the universe is built to be full of life eventually, and you are just here in the prologue, looking around and mistaking not yet for never? The universe might be built for life, but the main event hasn't really started yet. When you look out with today's telescopes, you see a mature cosmos, galaxies everywhere, stars everywhere, planets everywhere, and it's easy to assume if life can happen, it should have happened already. But that's not how cosmic history works. The universe has chemistry, and chemistry has a timeline. Early on, right after the Big Bang, there were only the lightest elements, mostly hydrogen and helium with a trace of lithium. No carbon, no oxygen, no iron, no silicon. All the stuff you're made of, all the elements that build rocks, water, atmospheres, DNA, they were forged later, in stars and supernovae. The first generations of stars were metal poor, in the astronomical sense, which means they couldn't easily build solid rocky planets like Earth. Only after many cycles of star birth and death did the concentration of heavy elements grow high enough that Earth-like planets became common. That ramp-up didn't finish in the first billion years. It took time. So when you ask, why aren't there more Earths out there making noise, you have to remember the universe spent billions of years just seeding itself with the elements needed to build those Earths in the first place. The phase where rocky planets with rich chemistry are abundant is not evenly spread over all of cosmic history. It's skewed toward the later part, closer to now and beyond. Now look at the stars themselves. Your Sun is a midlife middle-mass star. It will last maybe 10 billion years in its stable burning phase. That is enough time for life, but it is not the maximum. Smaller, cooler stars, red dwarfs, can burn steadily for trillions of years, orders of magnitude longer than the age of the universe so far. Most stars in the galaxy are actually these small red dwarfs, not sun-like stars. That means most of the habitable zones, most of the long-term stable real estate is around these tiny, long-lived stars. Right now, the universe is only 13.8 billion years old. That sounds huge, but it's nothing compared to the lifetimes of red dwarfs. Those stars will still be shining when the universe is hundreds of billions, even trillions of years old. If life can arise and persist around them, then the majority of all the time available for biology and intelligence is still ahead, not behind. By that measure, you are early, very early. Now fold in the delay we already saw on Earth. This planet has been habitable in some form for billions of years, but technological intelligence showed up only in the last tiny slice. For most of Earth's history, there was no species that built tools, no radios, no telescopes, no industry. It took around 4 billion years to go from water and rocks to a species that can even ask about aliens. That means, even once you have a nice metal-rich star and a rocky planet, you still need most of that planet's habitable lifetime before something like you appears. So imagine a typical rocky world around a long-lived star. It might form a bit later than Earth did, it might spend billions of years with just simple life, and it might not hit its intelligence moment until very late in that star's life. For many of those planets, that moment might still be billions of years in the future. From your current vantage point, those worlds are quiet, not because they will always be quiet, but because they're still in their microbial or pre-technological phase. This leads to a strange but important twist. If intelligent life tends to appear late in a planet's habitable window, and if the majority of habitable windows belong to tiny stars that live for trillions of years, then the natural time for civilizations to exist is not now, but much later. You might belong to a very rare group of early arrivals, civilizations that manage to appear in this relatively young universe, before most of the good seats have been occupied. If that's true, then of course you look around and mostly see emptiness. The other civilizations that will eventually fill the galaxy just haven't formed yet. Their planets are still cooling, their oceans are still simmering, their microbes are still experimenting. You are like someone walking into a stadium hours before the main event, looking at the empty seats and saying, "I guess nobody's coming." This is another kind of anthropic trap. You can only exist at a time when your environment has already produced at least one technological species, you. But that doesn't mean it has had enough time to produce many others. You're sampling the universe at a particular moment and then trying to generalize. If this moment happens to be early in the long arc of habitability, then your data will naturally say very few civilizations, even if the long-term answer turns out to be actually many, just later. So when you ask where is everybody, there's a serious possibility that the honest answer is not here yet. Not because life is impossible, not because intelligence is forbidden, but because the universe needed billions of years to build enough suitable planets And then those planets needed billions more to climb the ladder from chemistry to culture. On that scale, your arrival is not late, it's almost premature. Now combine this maybe your early idea with everything else you've already seen. You know that habitable planets are not trivial. They need the right star, the right orbit, the right chemistry. You know that abiogenesis might be hard or at least rare. You know that complex life takes time, intelligence is not guaranteed, and technological phases might be short and unstable. On top of that, you now see that the long-lasting red dwarf-powered part of the universe's habitable era is still basically empty of observers, simply because not enough time has passed. That stack of facts creates a sobering picture. In the far future, the universe might be dotted with many civilizations, spread around long-lived stars, quietly using channels and technologies you can barely imagine. But here, in this relatively young, still settling epoch, there might be only a few, or just one, active technological species in any given large region of the galaxy. You might simply be one of the first. And that brings you to the core punchline of this whole argument. When you add scale, light speed limits, rare planets, origin of life bottlenecks, evolution's indifference to intelligence, self-destruction risks, detection biases, deliberate silence, limited instruments, and cosmic timing, you get a universe where contact is not just unlikely, it is practically impossible for you, here and now, even if the universe is ultimately full of minds. So the real question is not, are we absolutely alone forever? It's, what does impossible to find actually mean for us in practice, given all these filters stacked together? And what does that say about our place in this galaxy right now? The universe doesn't have to be empty for you to never meet anyone. That's the part your intuition keeps fighting. Look back at everything you've walked through. First, the raw scale problem. You live in a galaxy with around 100 billion stars, inside a universe with maybe 100 billion galaxies, and you've only sampled a microscopic fraction of that. Then the light speed problem. Every interaction is delayed by years, centuries, or millennia, so even if someone is talking, you hear them long after the fact, and any reply is a message to a future they might not survive to see. Then the planets. Yes, worlds are common, but truly stable. Earth-like planets with long, calm, habitable histories are probably rare. Then the origin of life, a step you still do not understand in detail. That may be easy or maybe almost impossible. And so far you only know of one clear success. Then evolution, which is perfectly happy to fill a planet with microbes and simple animals for billions of years, without ever bothering to create a species that cares about radio telescopes. On top of that, you have the great filter idea. Maybe most of the brutal steps are in your past, which would make you an extreme outlier, or maybe the worst step is in front of you, in the form of self-destruction before you stabilize. Then physics comes in again. Signals fade with distance, get distorted by the interstellar medium, and are easily buried in noise. Timing kills you too. Civilizations are short flares on a 10 billion year background, and their peaks barely overlap in space and time. The galaxy itself is not safe. Supernovae, gamma ray bursts, orbital disturbances, and long-term chaos wipe out or reset biospheres. Any species that understands game theory has a strong incentive to go quiet, to hide their emissions, to use tight beams and channels that look invisible from far away. And you, with your tiny telescopes and narrow search strategies, are staring through a pinhole mostly tuned to signals that look like your own outdated technology, while real advanced tech might blend into natural noise or operate in domains you don't even monitor. Now stack all of that together. Don't just list it, multiply it. Distance and light speed / your practical reach. Rare habitable worlds / the number of good starting points. Abiogenesis bottleneck / the number of living worlds. Evolution's indifference to intelligence slashes the number of technological species. Self-destruction risks and short high-tech lifetimes / the overlap in time. Detection limits, signal fading, and strange encoding / the number of signals you can actually pick out. Deliberate silence slashes what's left. None of those factors has to be absolute. None of them has to be 0 or 1. They just have to be small probabilities that cascade. You can easily imagine a galaxy where, over billions of years, 100 or 1,000 technological civilizations arise. On paper, that sounds like a crowded Milky Way, but when you spread them out across 100,000 light years and 10 billion years, give them short, visible lifetimes, and hide their signatures behind physics and strategy, the odds that you and any one of them are close enough, active at the same time, using compatible tech and looking in the right direction, with the right instruments, at the right moment, crash towards zero. That is what impossible in practice really means here. Not that the laws of physics forbid other intelligences, not that there is a rule that says only one mind per galaxy, but that for you, standing where you are, with the tools you have, the chance of actual contact is so small that you can treat it as zero over the lifespan of your civilization. You could search for thousands of years and still get nothing but silence, even in a galaxy that has hosted many civilizations across its history. So what do the actual data say so far, when you strip out wishful thinking? You've confirmed thousands of exoplanets, you've measured some of their atmospheres, you've modelled their climates, but you have zero confirmed signs of life and zero unambiguous technosignatures. No obvious industrial gases, no clear artificial lights, no repeating narrow-band messages that scream this is a transmitter. That does not prove you're alone. It just proves that, given your current methods, any other civilizations are either too far, too quiet, too rare, too short-lived, or too well hidden to show up. What about the famous question, where is everybody? When Enrico Fermi asked that, it sounded like a paradox. If the galaxy can make lots of civilizations, and they can spread, why don't we see them? But once you bring in all the filters, that question stops being a paradox and becomes a warning about your expectations. You're expecting the universe to be dense, noisy, and convenient, like a city full of neighbours shouting across balconies. The reality is closer to a huge desert, where a handful of camps appear at random times and vanish again, and the odds of two camps ever seeing each other's fires are tiny. The universe is under no obligation to match your gut feeling. It doesn't care that empty skies feel wrong to you. It doesn't care that your stories and movies have made you expect crowded star maps and galactic clubs. It follows its own rules, slow, indifferent, and brutal about time and distance. Once you accept that, the paradox dissolves. Of course, you don't see anyone. The default outcome, given all these constraints, is that you don't. So you end up on a knife's edge. On one side, the possibility that you're terrifyingly rare, the result of a chain of low probability events that almost never line up, a civilization that slipped through a great filter that kills almost everyone else. On the other side, the possibility that you are one of many, but separated from the others by distances and time so large, by physics so unforgiving, and by behaviour so cautious, that you will never share a single live conversation with any of them. In both cases, your day-to-day experience is the same. You look up, you build bigger dishes, sharper telescopes, smarter algorithms, and you hear nothing but the natural universe. The silence is not proof of emptiness, it's just what it looks like from where you stand, and that's the real punchline. The universe doesn't have to be empty for you to never meet anyone. All it has to be is large enough, old enough, hostile enough, and quiet enough that for your brief moment of existence with your limited reach and fragile tools, everyone else might as well be myths. In theory, they could be out there. In practice, for you, they are impossible to find. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.